Welcome everyone. Today we have a seminar from our very own, in a sense, Milan Curcic. And Milan has been here, he got his bachelor's degree in meteorology at Belgrade in 2009 in meteorology, but working on the numerics of an ocean model. He came here to work with Dr. Shui Chen at that time and built probably the first momentum conserving atmosphere, ocean, and wave model. Many of us aren't used to thinking of the wave field as a third reservoir for momentum, one whose transport is, radiation. So anyway, momentum radiation. So he worked on that, and that model has gone on to have applications, but he turned somewhat to observations more. Here he's had postdoctoral positions here and at the University of Washington, and worked maybe increasingly with observations as well. And now he's an assistant scientist here. And I think what ties it all together is computation and coding. And I would just say for myself, Milan is very strong and very generous in the realm of coding and computation. And if students who haven't learned this yet, there are literally orders of magnitude of productivity to be gained or not from your power and or ability to access this sort of generosity in the space of computation and coding. So I've always felt we're very lucky to have him around, and he ran this Lunch Bites seminar for a long time and really contributed a lot to the culture here of students upping their computation game. Just years of productivity to be gained from this sort of thing. Sounds like he's back to modeling here, but I'll let the title and the speaker speak for himself. Welcome, Milan.
Thanks so much, Bran. This is a wonderful intro, and thanks all for coming. I'm grateful to have this opportunity to speak to you all. I feel like being at home here. All right, just a little bit about me. Bran already gave a good intro, but I'm an assistant scientist here at UN. I consider myself both an oceanographer and a meteorologist, and work at the intersection and across the interface. I'm also a technologist and keep up with the technology and computational tools, especially as how they relate and help us advance science. I also wrote a programming textbook, and you can learn more about me at my webpage. And just real quick, since I mentioned the book, published in 2020, it's highly rated, sold over 3,000 copies, and I'd like to invite students to email me. First 5 students to email me will get an author's copy of my book. All right, so a few themes of this talk that I hope to accomplish is the relationship and the tight dependency between theory, observation, modeling, inner field and broader. The relationship and the complementary nature of field observations and laboratory observations. Neither one is sufficient. We need both to work together. And likewise, traditional numerical modeling on one side and machine learning is becoming promising with innovative methods to advance science. Okay, so let's start at the beginning of my story here at Rosenstiel. This is a video from an unmanned automated vessel by sail drone inside Hurricane Isabel. And what you see here are very strong winds blowing over the waves. Waves are steep and high, they break. You see streaks, you see a lot of foam, spray generation. And my main takeaway here, these are very complex processes that we are attempting to model toward improved atmosphere wave ocean prediction. But because of the complexity and the difficulty to measure these things, we lack data, we lack understanding. So we're pushing on those fronts to advance our knowledge and predictive capability. So when I first came, my advisor, Professor Shui Chen, she basically posed me a challenge, and that is one of the several aspects in which our models are deficient in predictive capability is the air-sea momentum exchange not being sufficiently resolved, momentum constraint, and so on. And that may be one of the key pieces needed for important processes that are difficult to predict, like rapid intensification of hurricanes. So air-sea momentum exchange is governed by waves, mostly, but most coupled models do not resolve waves. And even with waves, so the models that do resolve them, they lack momentum closure. So my challenge was, can we achieve momentum closure in a coupled atmosphere wave ocean system? So we started from primitive equations. These are specifically momentum balance equations. The top one is for the atmosphere, the bottom one is for the ocean circulation. You see that they're almost exactly the same equations, but they are different in terms of details. So here in the top equation, I use subscript A to denote atmosphere for air, and W in the second equation to denote water. But the terms, the terms that we're used to, advection, pressure gradient, Coriolis, they're common to atmosphere and ocean. And most of the details, most of the computational time that is spent in models is really in the subgrid scale unresolved processes. And these are typically parameterized with heuristics, so based on data, so they're empirical parameterizations. They can often be crude, computational intensive, and often biased for certain weather or ocean patterns, and so on. And what I pulled out here on the right-hand side is the vertical flux of horizontal momentum, or the Reynolds stress term. And at the very surface, they pose a boundary condition, lower boundary condition for the atmosphere, top boundary condition for the ocean. So the simple and obvious thing to do is to say these must equal at the surface. So you end up with tau atmosphere equals tau water. And this is an obvious and mathematically correct solution. But what about waves? We're currently not resolving waves so far. And this is a concept that my thesis introduced, and that is when the wind is blowing over the ocean, the waves are growing, and they're inducing this stress term, which we denote tau atmosphere. And the key new thing here is that the wind, what we know as wind stress, is different from the ocean stress that the ocean circulation gets from the surface. Because as waves grow, they take up momentum, and waves propagate, they export momentum horizontally. So there is some, if you consider waves as the real world does, there is some momentum deficit that is being exported by waves and that is not delivered to the ocean. I also here show these orbital motions induced by waves, which on average result in a Lagrangian so-called Stokes drift, and I'll talk a little bit more in a few slides. And I just want to point out that waves are responsible for quite a few important processes in the Earth system. Waves grow, they induce wind stress, and induces in part atmospheric boundary layer mixing. On the ocean side, when waves break, they induce upper ocean mixing, and that leads to vertical transport of gases and nutrients. And likewise, Stokes drift, which I just mentioned, is responsible for length meter circulation, which are these organized cells in the near surface ocean that induce even more mixing, to name a few. So enter wave energy balance. This is how we typically resolve waves in regional to large to global scale models. Waves are represented as a spectrum of energy, and that energy is resolved in wave number space, so from long waves to short waves, and also in directional space. And this essentially, the whole left-hand side is a total derivative, where the second, third, and fourth terms are basically advection terms in geographical space, so that's wave propagation, wave number space, that's the downshifting in the wave number space, and in directional space, which is refraction. So when waves approach the coastline, they turn toward the shallower part of the nearshore. On the right-hand side term, we have so-called source terms. So these are parametric, and they describe how waves grow when the wind is blowing over, how waves break when they become too steep, and how they transfer energy between each other. So now when I plug in this equation in between the atmosphere and ocean momentum balance, I can connect the stress terms with the wave growth source function and the ocean stress term to the wave dissipation function. And this is how now we can track this momentum that is lost at the atmosphere's surface through waves. Some of that momentum is being propagated away, but some of it is delivered to the ocean top. I mentioned Stokes drift earlier. This will give you an idea of what it looks like when waves are moving. The water particles are following orbits, but the orbits are not closed. So over time, you have this net drift of material going forward. And Stokes drift actually introduces two more terms in the ocean momentum equation, specifically the Coriolis-Stokes. That's the Stokes drift contribution to the Coriolis force, and the vortex force. Vortex force is responsible for tilting the vortices in the ocean, which leads to laminar circulation. And without these terms, it's known that most climate models have upper mixed layer too shallow in the Southern Ocean, and that's where the waves are highest and steepest and most active. And introducing these terms actually improves the mixed layer depth in ocean components of climate models. So this is not only relevant for small scale stuff, but also global and climate. All right, so the implementation took form in Unified Wave Interface couple model. I used WAR for the atmosphere, University of Miami wave model for waves. So this was developed together with Professor Mark Donlan here at Rosenstiel, and HICOM for ocean circulation. ESMF is a software framework that lets you put together these components, do interpolation, parallelization, and so on. And this was deployed and ran in an operational setting here in quotation marks, because we weren't operational in a true sense of the word, like public agencies do, but in a research setting. The model was running in real time, and it was providing products to teams who were doing field work during field campaigns. And this was deployed on iDisk systems, NASA and DOE supercomputers, and was used in support of 5 major field campaigns. And I do want to point out that a later iteration of this couple system I've been working on for the past few years, and is in continued development here at Rosenstiel, and also being tested on iDisk Triton. So key findings. Basically, I simulate 4 different tropical cyclones: Ike, Earl, Fanapi, and Isaac. 4 different ones because I want to see if these patterns translate between different storms of different intensities, different structures, and so on. So these are 10-meter winds, what you expect to see of tropical cyclones to look like. And these are the wave patterns that they produce. So this is sort of a typical kidney-shaped pattern of wave height that forms on the right-hand side of the storm, because waves there are in resonance with the storm motion. And now the relationship of wind and stress, which is governed by waves, becomes very interesting, because they're not necessarily aligned once you have waves in the system. And you can identify waves aligned with wind in blue, waves opposing wind in red, and waves outrunning wind in green. And the main takeaway here is that between the 4 storms, they're all kind of similar, but they're all different. They all have different structure, size, and you have regions in each storm where all 3 regimes exist at the same time. This is difficult or impossible to parameterize. Simple heuristics don't work. So we need either explicit modeling, which is expensive, or machine learning, for which we need data. And I mentioned this momentum deficit that you have when you introduce waves, and here I'm plotting the ratio of the ocean stress to the atmosphere stress, and blue is everything under 1, which means that wherever you see blue, that means that some momentum is being taken away from the storm and not being delivered to the ocean, relative to what you had in the traditional system. And these are just some of the applications that these models have had since. I won't go through all of them. I will only do a little show and tell on the first one, wave impacts on ocean transport. And I do also, besides this research applications that this has had, I also want to point out that part of this has even made it into NOAA's operational wave watch tree model, specifically the stress calculation from our wave model. So this shows you impacts both on research and operations. And I just want to show a quote, which is was a motivational pickup for me very early on in my PhD by Ashwin Srinivasan. Model development initially seems a thankless task. You can work on it for years. Anybody would see it like you're not doing anything, but once it works and people start using it, you get cited a lot. And that's what happened. So long term, it's worth it. All right, so I'm going to say a little about the impact of waves on ocean transport. So in 2010, we had the Deepwater Horizon accident and oil spill in the Gulf of Mexico. And here on the right is a satellite image after the fact of what the oil spill looks like. You can see it on the ocean surface. You see a filament of it getting entrained in a mesoscale ocean net. So this is a big deal for the ecosystems, for marine life. And to address the question of where does the oil go and what happens to the oil as it's being emitted from the hole at the bottom and as it gets to the surface, led by Professor Tamaios Gokmen here at Rosenstiel and a consortium of a dozen or more universities and institutions, was the CARTH consortium. And I was very lucky to work as a PhD student for a few years on CARTH. And in 2012, CARTH deployed 300 surface drifters in places near Deep Horizon. And a month later, Hurricane Isaac propagated over this cloud of drifters, about 200 drifters. So this is the track on the right. Red is our simulated track with a couple model, and the black trajectories are drifter trajectories. And what we can do here is really powerful. The model allows us to separate the components from mean ocean currents and from wave drift, whereas the drifters just tells us what was the total. From drifters, we can't tell individual components, but it can tell us what's the true that the water is moving. So here are differentiated in red. The Lagrangian velocity is the sum of Eulerian, which are the mean currents, and the Stokes drift. And on the right you see the black trajectories of the truth again, and red and green are simulated trajectories with and without waves. You see in many places that they're similar, but also in many that they are very different. For example, if you look at just these here, and that tells you that initial ocean conditions in the models are very important. If you have small errors, they compound over time, it's a chaotic system, and your Lagrangian predictions can be very different. But we can look at what's the transport due to Stokes drift only on a regional scale. And if we do that and simulate trajectories using just Stokes drift during the hurricane passage, it turns out you get a counterclockwise drift on the right-hand side. That's clockwise, sorry. And counterclockwise on the left-hand side. But there is a very distinct and asymmetric pattern here that has been previously unobserved. But if we pick a group of drifters that have been predicted pretty well, meaning initial ocean conditions were good, that's a good case for us to see the effects of Stokes drift alone. And here again, red is the full velocity, Eulerian is the velocity without the wave contribution. And you see that to reproduce the observed trajectories, you really need wave contributions in there. And this is the averaged velocity over the entire drifter set. So black is observed again, and red is the modeled velocity with contributions of waves. And you see that Stokes drift accounts up to about 20% to the ocean velocities in very high winds. Another very high impact result from this was the diffusivity as function of scale, which historically has been known to follow this 4 to the 3 power law. So on the left-hand side is the diffusivity, which is basically the rate of spreading of material. And the x-axis is the scale. And you see that historical measurements follow this line, and the black circles are the diffusivities from drifters before the hurricane. So they also follow the same line. But during hurricane, actually we find that the diffusivity got elevated across all scales by an order of magnitude. And the stars here indicate the entire, basically the larger scale that we could get, which shows you the impact that during the hurricane passage, it's very large. Once the hurricane has passed, it recedes back to the expected log. So what are we still missing? Waves and stress remain difficult to measure in strong winds. We have little clue how large is air-sea drag in major hurricane force winds. The models are pushed to the limits, but we need data. I was fortunate to work closely with Mark Donlan in the first few years of my PhD, and up to that point I was doing only modeling, nothing else, and Brown House was offering his course in air-sea instruments and measurement techniques. So I asked Mark, hey, what do you think? Should I take Brown's course? Looks interesting. And Mark thought for a second, then he said, a great scientist should be versed in theory, experimentation, and modeling. That was his answer. So I took it and said, yes, I should take this course. And basically it was a message for me that I need to broaden in my scope. And that brings us to the Sustain Lab. And to show you why joining the Sustain Lab was a good idea, I should just show you this video, which is right here in the other building on campus. And it just shows you the conditions that we can create in the lab. These are Category 5 hurricane force winds and waves. You can see the surface, and this level allows us in a finely controlled setting to place instruments the way they want them and to capture exactly the quantities that we need. So the main question for me was, what's the magnitude of air-sea drag in extreme wind conditions? What physical processes govern it? And this was supported by an NSF grant that was my first grant that I wrote with the help of Brown House. I was very lucky as my first proposal that it was granted, but it was a very good proposal, but we were also lucky in the sense that we were at the right time in the right place. It was an itching question, and we had the lab to do the task. This was the first output from our project, and first we did work in the small tank to attempt to reproduce established results by Mark Donlan from 2004, which was discovery of drag saturation in high winds. This just shows you the lab setup and what it looks like in person. We have multiple sensors in here, wave gauges, pressure gauges, velocity sensors, and so on. So a lot of instrumentations that can get us the full picture in terms of what's the drag coefficient in high winds. And it turns out we were able to reproduce the saturation. The saturation is here as drag coefficient increases with wind, at some point it stops increasing, it flattens. Do you get this? So black are the original results by Mark-Donnell and al. So they lay a bit lower relative to the field measurements by Edson et al. And note that the field measurements stop here. Basically, past this point, past 25 meters per second or so, it's very difficult to measure this stuff in the field. So one question is, why didn't we reproduce Mark-Donnell's results in the same lab, but we are much closer to the field? So I had to dig deeper. And I actually found a source code error in 20 years old MATLAB code. And it was just a typo. And I made a fix and I reran the calculation with the original data. And what happened was that now the original data went up, and now in this range, 10 to 25 meters per second, it actually has a really good match with the field. And this was kind of a big discovery, because up to that point, prior 16 years, WRF has implemented this as a parameterization scheme in their surface layer. More than a dozen published studies use this result for their hurricane studies. So this is a big deal. The takeaway is still the same, the drag saturates, but the magnitude is different. And this was picked up and featured in a Nature Technology article that basically emphasized the need for open software data and science practices. If the code was open source, if the data was open back in the day, this would have been discovered earlier. And my takeaway from this is that it's no longer sufficient to publish papers and data. We must publish data processing and analysis code end-to-end, which means from raw data to the figure. I also want to feature the work of our student, Payson Tan, who is here in the room, and he's doing great work in the lab and in the field, who really dug deep into the physical process of wave growth and aerodynamic sheltering that can lead to drag saturation. And what he found is that this sheltering coefficient, which is a parameter in wave models, which has been considered a constant, a tunable coefficient, actually varies tremendously, both with wind, but also with background wave states, which really emphasizes the need for us to rethink how source terms in wave models are formulated. Payson's paper was just published a month ago in JGR Oceans. And this is another one of his key results, which basically shows that the shortwave energy is focused on the rear face of the wave. So this is the phase of the long wave, and the shortwave energy is focused on the windward side. But the steepness of waves appears in both windward side and leeward side. And these are different processes here at play. We have strongly forced short waves on this side and wave dissipation on a steep side of a long wave on this side. And this is just an image from a camera showing you what it looks like from the side. And I just want to show you some ongoing work from the big tank in Sustain Lab. So all the magenta points are our recent measurements in the lab. And what I've added here also are field measurements of drag in high winds. Now recall, I said that there are no field data past 20-something meters per second. Well, there's no direct field data, but people make estimates of ocean drag based on upper ocean momentum budget from floats or from GPS drop zones, and they get these estimates. And all this data, which you see has very, very broad spread, high uncertainty, has actually led sort of an alternative hypothesis that drag not only saturates, but drag may actually decrease in high winds. So far, we don't see that in the lab, but we do see this very high discrepancy that we can't, but we must reconcile. As in, Y lab shows about 3 at 50 meters per second, whereas the field ocean data shows about 1.5. And we're preparing this for publication in GRL to submit very soon. And I just want to illustrate this this discrepancy. Basically, on the y-axis here, I'm drawing environment fidelity, whereas field data really measure the process that we're looking for. Whereas laboratory is sort of an idealized setting. So we're trying to the best of the laboratory abilities to reproduce the real process out in the real ocean. But there are limitations, of course, such as limited fetch, limited depth, and so on. So measurement fidelity is actually on the x-axis. So laboratory observations are high up there, but our axis of improvement is really on the diagonal. We need both environment fidelity and measurement fidelity. So by moving lab observational techniques closer toward environmental fidelity and field observations to higher measurement fidelity will get us a much better understanding of what's going on. So switching more to field work, I've been very lucky to be part of the Coastal Land Air-Sea Interaction project past 3 or so years. And Class C basically executes field campaigns toward coast-aware air-sea flux parameterizations for operational weather models. So this is not necessarily hurricane winds, but it's more about coastal flux, which is just as unknown and variable as hurricane conditions. We had 4 field campaigns so far, and the key item from our group is the deployment of 8 air-sea interaction spar buoys. So these are designed to be stationary spar for short waves, but pitch and roll buoys for long, so we can capture the whole spectrum of waves. And they're really optimized for flux and wave measurements with minimal flow distortion. So they're really optimized for the quality of the flux and wave measurements. And they're equipped with many redundant sensors for motion, wind velocity, wave sensors, to give us very good estimates of both flux and meteorological parameters. And I'm just going to show you what it looks like. This is really, really difficult and long work to get these buoys built. We build them in the shipyard, put them on ships. The ship takes out 2 at a time. So we did Monterey Bay and Gulf of Mexico. This is a picture from the recovery. I'm right here. This is a picture from a master's student in the lab, Jill. She was in a part of the small boat operations, and she took this great picture of Roger Vell and ACES. This is our group from UM. And here I just want to feature our students, Sam Medina and Payson Tan, who've been doing a really great work in the field as well as lab. And I also want to emphasize the need for students and early career scientists to have these opportunities to go to the field, whether ocean or atmosphere, get their hands dirty, work with instruments, and really feel the ocean and the atmosphere. But it's not only students who learn a lot. I also learned a ton from this. I didn't do field work before then, and actually on the last cruise, I'm very grateful to Brown House who have given me the opportunity to be a chief scientist on one leg of the cruise, which was a huge learning for me. And this is just a snippet of what our data looks like, time series of wind and wave height from our latest Gulf of Mexico deployment. You see fronts passing by from the north, and you see wave heights growing in response to that. But what we're really going after is the flux and its dependence on wind as well as other environmental parameters. This scatter looks simple, but a ton of work went into producing this scatter, and we want to parameterize this to put in the models. That's our task after all. And this is a perfect candidate for machine learning methods. and I'm going to show you just one example of how that works. Basically, I can construct a neural network and pick the input parameters that go into it. And here I chose wind speed, significant wave height, mean period, and air seat temperature difference, which is related to thermodynamic stability, and fit this input data to produce a function that best outputs the flux. What you see here on the left, black is the data. There's about 30,000 points here. And red are model realizations when I feed in observed input data. So you see that it produces, to an extent, both the spread, it produces this bimodality in high winds. So it really has a deep richness on information in it, at least based on these four parameters, where the spread is not captured, so those have to be covered either by other parameters or just unexplained variability. And to show you the power of this for understanding the process, now that I have this model, I can basically put any values of these parameters into the model. And so I can vary, for example, the air seat temperature to basically simulate neutral, stable, and unstable thermodynamic conditions, and to see how the flux, as captured by the model, responds to that. So we get basically higher stress for unstable and lower stress for stable thermodynamic conditions, which is what we expect to see. And just a note here, neural networks are, they're known to be universal function approximator, which means that for any function, arbitrarily complex, there is some neural network that approximates it accurately. So I'll give you a quick intro to machine learning from here. I find it surprising. It's actually difficult to find a very simple and short explanation of what it is. I'll give you a 20-second explanation. So in traditional modeling, we prescribe a model that takes an input and we get the result on the other side. In contrast, machine learning generates a model for us, generates the relationship based on sets of input and output data. So we need to have inputs and outputs to create this model. But once we do that, the model ideally will work generally on new data. And I'll talk more about neural networks. That's a specific data structure and a method that is part of the so-called supervised machine learning. And basically, we build these layers of so-called neurons. So on the left, you have the input layer, and in between, you have the so-called hidden layers, and you can play with more layers to construct, to add more depth to the model, to capture more complex patterns. And the output layer is, whatever you're trying to predict. In the forward pass, you do the inference, you do the prediction. But the backward pass, which is basically equivalent to an adjoint model of data assimilation methods, is how you can change the weights of the model to basically fit the model toward the solution. So why machine learning for earth science? There's at least 3 reasons. It helps us discover patterns in complex data. That means new scientific understanding. It helps us build models from data, and it can do that in an unbiased and more accurate way because we no longer have to assume basis functions like, is the data quadratic, is it exponential, is it a log? We don't have to assume anymore. And also, machine learning can help us emulate and accelerate explicit and expensive models. So that should give us faster and more general models. Checking the time, okay. So one recent example of sort of on one end of the extreme where you go full on deep learning to create a predictive weather model is ForecastNet, which came out in 22, which basically it was trained on ERA5. It has really, really good, pretty good scores relative to the state of the art in machine learning. but it executes at 10,000 times the speed of a traditional model. Now, there are limitations here. This is not a replacement for the full model. And basically, whatever data set you take that you train it on, so core degree resolution, 6 hourly time step, that's what you're going to get. You only get core degree, you only get 6 hourly time step, and you only get the variables that you train it on. You can't say, oh, how about it at this time in between, and how about this other variable? It can't give you that. So this is useful as a quick forecasting tool, but not a replacement. And some alternative approaches are physics-informed neural networks, where actual physics terms get emulated by neural networks, or by emulating subgrid scale processes. So these are the really expensive parts and highly parametric parts of ocean and atmosphere models. So think cloud microphysics, boundary layer turbulence, upper ocean mixing, and such things. So integrating machine learning in Earth system models is challenging. We have a two-language problem in practice. Machine learning training is typically done in Python frameworks. Python frameworks are most mature for this stuff. But virtually every weather, ocean, wave, climate model is written in Fortran. This is not only a historical thing. I just came from a wave meeting, WISE, 2 weeks ago, where NOAA researchers and model developers presented their next generation state-of-the-art community Earth system models. And guess what? They are all in Fortran. So this two-language problem is a point of friction for integrating ML into Earth system models. And some possible solutions are, you can rewrite Earth system modeling in another language. This is both difficult and expensive. It has not been done before. We can interface Python machine learning directly from Earth system models. This is difficult from a maintenance and performance perspective. We can glue Python machine learning with Earth systems with data files. This works, but it's kind of clumsy. Or we can implement machine learning, which is as big and developed as it is, it's an order of magnitude smaller than the weather and ocean enterprise and those code bases and all the physics in there. So this is easy, but it needs work. So to solve this, I created a neural Fortran, which is a parallel deep learning framework for Fortran applications. It can do both training and inference, or arbitrarily deep, dense and convolutional networks, and it already has a track record. It's been used in over a dozen published studies to accelerate models from chemistry, combustion, weather, and climate. And so it's been supported in part by a small grant from NASA Goddard, and also we just got a student intern contributor funded by Google Summer of Code program, which basically funds newcomers to the open source world to contribute on a project and learn. I also want to feature this DOE effort, which is still at the LOI stage, and we're hoping for a positive answer, but it is very much on topic, and it's an organized effort to evaluate the feasibility of deep learning emulators for subgrid scale processes or system models. So basically this should take us toward more general and efficient models, led by me at the University of Miami and in collaboration with the Berkeley Lab, NCAR, and industry partners. And I talked a little bit about open source, but I do want to advocate more for it, especially to all the young scientists in the room who still have the energy and the time. FortranLang is an open source community aiming to build modern tooling and nurture library ecosystem for Fortran. And basically, Andrei Chertik from, at the time, Los Alamos National Lab, and I got together and decided to organize and basically build this open source space because there was a lot of need for people to get the Fortran tooling and libraries up to speed, because we have all this legacy infrastructure in the weather enterprise that has been developed before the internet era and basically before the time that people communicated electronically. So things were developed much slower back in the day, and now the new languages, new communities, they have a head start by starting in the modern era with internet, GitHub, and so on. So we decided to make the same effort, but for Fortran to make it easier for new and young scientists going into the weather enterprise and into weather model development, because they will be working in Fortran, that they have an easier job working with that. So these are some of our flagship projects: the standard library, the package manager, and the community website. Have an active collaboration with the Fortran compiler, which is a new compiler that targets multiple architectures, and also the standards committee, which I'm also an alternate member of, thanks to the invite from Gary Klimovitz at the time of NVIDIA. He's been supported by Google Summer of Code 3 years in a row, 15 paid student internships to date, and last year he was awarded a $200K pilot grant from the Sovereign Tech Fund to further these tools. So this just shows you an impact that open source communities have when you provide a space for people to collaborate on the same problem. And Fortran has also been provisionally accepted as a non-focus fiscally sponsored project, which some of you may be familiar with if you work with Python. And just to show you an example that this is really a technology for the future and not something from the past, my slides are running in the browser, and the Fortran compiler is running in the browser in my slide. And this is the code on the left. It's just an example Mandelbrot simulation, and it's outputting this image. And the code compiled in 180 milliseconds and executed in 185 milliseconds. So just imagine a classroom setting, putting in a simple small climate model for students to tweak, play with, and display output in real time as they're editing the code. That's the power of it. I also want to feature Cloud Drift, which I've been working on with Professor Shen Elipo here for the past 9 months or so. Cloud Drift is a Python library that aims to accelerate the use of Lagrangian ocean data. It's built on top of the X-array data structure. If you use Python in geosciences, you probably also use X-array. And this library provides common oceanographic analysis functions and also readers for custom Lagrangian dataset. And it's funded by NSF EarthCube. Of course, it's open source too. You can go to GitHub, get the code, play with it, and do cool Lagrangian analysis. Okay, I just want to mention some fundraising opportunity. I hope to be able to apply for NSF Career. And the other NSF, ONR, DOE, and NASA are either at the LOI submitted stage or in progress planned. So this is important to keep going and keep bringing the funds so we can continue advancing the science. And I just want to list and thank my collaborators from the university, other universities, national labs, and the industry. And okay, these are my takeaways. More as an advice for young students: work on long and hard problems. It pays off, even if it's intimidating and often frustrating. Modeling alone is insufficient. We need measurements in tandem with modeling to advance understanding. Likewise, laboratory and field are complementary. They each serve their important purposes, but the closer we get to a unified view, the better we'll get. And likewise, machine learning and traditional models are most powerful when used together. They are not at odds. I don't believe that machine learning can completely replace traditional modeling, but it can highly enhance it and augment it. And especially for young people in the room, invest time and care in open source, open data, and open research. It pays off to be able to go back 5 years and see what you did because you're trying to figure it out. You know exactly where the data is, you know exactly what the code is. You can run with the click of a button, it works. And thank you. Questions welcome. Brian.
I liked your work in progress of figuring, doing the lab measurements of the drag coefficient, and wondering if machine learning can develop a model to get at that, because this has been a long-standing issue of what happens at higher wind speeds, and it doesn't seem to be getting close to being answered because your measurements don't really show it plateauing like some others have, and are we closer to knowing that?
I thought about whether machine learning could help here. So both field data, at least in high winds, field data are very sparse. There aren't that many data points. Machine learning really needs a lot of data to build something useful. Likely for the lab, but with the lab we are possibly, because of limited conditions in terms of wavelengths that we can reach, the water depth, the fetch, all those factors, it could be that the variability is not fully captured. The variability from the field is not fully captured in the lab. So I'm not convinced that machine learning can specifically help with these data sets, but I think it could help with pulling out the nuances of what contributed to drag going up or down or leveling off, because we can feed in whatever parameters we want. We can feed in any wave parameter. We can feed in ocean current in there, wind, stress. So I believe it can help with the understanding of the mechanism. Manesh?
I have 2 questions. One, is there like a physical explanation for why it saturates, or is that still sort of?
There are a few working hypotheses. One is that the waves are basically, the waves themselves in terms of steepness is saturating, they're breaking, so they're not providing additional roughness. The tops of wave crests are also at that point being blown off from direct impact from wind, which adds additional dissipation to the waves. There are sea spray hypotheses that they suppress the vortices in the air in the surface layer. So there are multiple working hypotheses. It's possible that they all contribute to an extent.
Yeah. And the other question, where you use the neural network with the scatter plot, so is that data from all of the surface buoys, and then, I guess my question is, if you fit the network with data from one buoy, does that model still work if you use it in a buoy that's in a different part of the ocean? Is it still?
Great question. So what's different about different buoys being in different parts of the ocean? And these are all, I didn't show the map, but they're all they're in different parts of the coastal region. Some are more further offshore, some are closer to the shore. But the key thing that's different here between the buoys are really the wave state. Waves may be shoaling at one buoy versus the other. They come at different angles relative to the wind. So the flux itself, as long as we're not getting, we don't have flux footprint over the land, say if you have offshore wind and you're too close to the coast, the flux itself shouldn't be aware of the coastline orientation. what the coastline and the bathymetry do is they change the wave field, and the flux responds to the wave field.
So that neural network is sort of generalized across all of those observations?
This neural network is 8 buoys, two field campaigns, about 30,000 data points.
So if you tried it like somewhere, I guess all the observations are in the same place, so you can't test if that works in a different coastal setting or something?
I have not tested it, but this is very, very recent development. Yeah,
It's really cool.
yeah. Thanks. Brian, do you have one?
Oh, as long as you're here. Well, so why is the bimodality there? If it's not delta t, one of those other inputs explains the bimodal fork.
I believe in part it is delta t, because
Okay. All right.
unstable delta t raises it up,
Yeah.
but I'm not showing it here, but it could be in the waves.
Yeah. Okay.
What curious thing about this is that for every training sample, for example here the 4 parameters are in a dynamical balance, so they are from an actual condition that
Yeah.
happened. So if you fix 3 and you go crazy with the 4th one, you're going out of the range of what the model was trained on,
All right.
and it starts to break.
Yeah.
So an important caveat about these methods is that you need to be in the range of what you trained on.
Milan, this is Tamay. Fantastic talk. I really
Tamay.
enjoyed the great seminar.
Thanks.
I have one funky question. You said that the easiest way forward due to this two-language problem is to convert all the Python programs in machine learning to Fortran. And my impression from all this ChatGPT mania is that ChatGPT some version can translate it. Is it true? Or will it, I mean, it's probably not as much work as even you try to say, which you said it's the easiest. What's your view on that?
Yeah, it's true, but ultimately, I think that boils down to whether you're using a tool to do a translation. Where I'm addressing more, how does it look like in practice and operations? Is machine learning on the Earth system component side, or it's something else that you're being interfacing? And yes, in part it's true that these tools can now generate mostly useful, often correct code. I found that they're very much like, I think they're analogous to an undergraduate summer intern that can often create good and correct code, but you do need to proofread it for correctness. You do need to test it, so it doesn't really remove you out of the equation.
No, but it can do, let's say, 70% of the work or 80% of the work very quickly.
Correct.
Yeah. Okay. Thank you. Great.
We have Dave Nolan in Zoom.
Dave, go ahead.
Yeah. First, I just want to be a professor and remind everybody that as far as the drag coefficient, people tend to forget that after CD there's a V squared, right? So even when like CD levels off, or even if it were to go down, like drag is still going up a lot. That being said, I want to ask you, Milan, your opinion. You know, in a period, I guess maybe over like 15 to 5 years ago, a lot of people jumped on board with the idea of the drag coefficient, not the drag, but the drag coefficient going down to high wind speed. I guess I can righteously say now for myself, I was always skeptical of that. But I wonder, do you understand why people jumped on board? So many people embrace that?
Good question. Yeah, I think it's probably a social, cultural, psychological thing. My hypothesis is that it's a change. It's a new result. And new result is more interesting than current understanding.
Okay. And based on your experience, or the results you have now, would you just rule that out completely, or do you think there's still any chance at like the very high end it goes down?
I don't want to ascribe chance. I don't rule it out for sure. I think we need to reconcile data from the lab and data from the field. And that's my key point here, is that neither give us a full picture on their own, and they give us different answers.
Okay. All right. Thank you, Milan.
Thank you.
And we have Mo in Zoom.
Mo, go ahead.
Hi, Milan. Great talk. I want to
Thank
take
you.
it back to the machine learning part, and if you could give us a little bit more detail about how you configure the system, and whether you do deterministic predictions with it, or did you add an uncertain components and you could actually reproduce the spread in the data itself?
Okay, you're talking about this specific slide, right?
Yeah.
Okay, so in practice, the setup was relatively simple. So I used a Python framework called TensorFlow, and you play a little bit with the network architecture, with the activation functions, with how many layers you use. In this specific case, I used, I believe, 3 hidden layers, 7, 5, 3 neurons. I only get one output in the output layer. Of course, the important part is you play with input parameters. You wanna capture as many input parameters as can reasonably contribute to flux, but you don't want to have strong dependency between the inputs. So you want it to be as orthogonal as possible. And yeah, actually training of this thing, it takes 30 seconds on my laptop for 30,000 data points, and for fitting a small network like this, it's a easy analysis kind of exercise. And in terms of the spread and whether it's deterministic or there's an ensemble, this is completely deterministic. So you can do ensembles by basically generating stochastic input variables and then assess the spread that you get out. But what you see here in the red scatter is I just took all the observational data that I had and I just feed it to the model. So if the model was perfect and if the model was completely representing the process that leads from inputs to the flux, I would reproduce the black dots. Basically, they would overlap. But not everything is in these 4 parameters, and there may be some unresolved variability in the flux that is not captured by anything that we measured.
Would you describe the model as being physics informed, since you boil the inputs to 4 parameters?
No, I don't think this is called physics informed. No, physics informed means more about embedding the dynamical constraints in the network itself. And this is purely data-based. So physics informed are a separate class of methods.
So how do you go from here, what you've done here, to actually subgrid scale parameterization with machine learning models, with neural nets?
Okay, so let's say we want to use this data set to make a surface layer parameterization specifically for the flux. One important aspect to consider is where is this going to be implemented? Is it in a strictly atmospheric model that doesn't have waves? In which case we cannot train and cannot give a model that's been trained on wave parameters, because the atmospheric model doesn't have wave parameters in it. So we need to be constrained to the parameters that the atmospheric model has as part of its state. So in this case, that'll be wind and air sea temperature difference, but we would exclude the wave parameters. And there's many other input parameters that we can use here for training from the in situ data sets. These are only a subset for illustration purpose. So this would not be my final model.
I realize that. Thanks. Great talk.
Thank you.
I just have one
Claire.
last question. Or maybe there's more questions, but yes, great talk. Great knowledge about your work. It's just a question about the open source models and experience with the Lagrangian model, that if you put it open source, you may not get any feedback. People take, but never contribute much. Have you experienced that, and how do you deal with that? Are you doing something different so that people actually want to contribute and feedback into the model?
Yeah, I think it's a matter of awareness and developing the culture. Open source is a relatively recent thing. It probably exploded with the start of GitHub around, I believe, 2008, 2009. So let's say 15 years. That's a pretty short time, and I find that young people who entered the field when open source was already around, when it was part of the environment, are much more likely to be active in it, and to contribute. And I think a lot has to do about a specific open source project. It could be a science software project, a model developed here. It's not sufficient to just put the code up there and it's available. What's very important is to have comprehensive and up-to-date documentation, clear instructions how to contribute, be very open and welcoming about it, and basically have some minimal amount of traction in terms of communication on the specific issues about the software that people can find, read, comment on. Yeah, so I think that's also a cultural problem.
Okay, thanks. Good advice.
Thank you.
John Van Leer has his hand up in Zoom.
Yeah, great talk. Really enjoyed it. Particularly the roll structure and the Langmuir circulation in the upper boundary layer. In shallow water, for example, in the Bahama Banks, there is a bottom frictionally driven regime that resembles Langmuir circulation, but is typically dominant, driven by tidal currents as a dissipation mechanism, I think you could say. And I was wondering, that's another way that you could lose momentum into the bottom boundary layer in shallow water. And the interplay between, I'd like you to comment on what you think the interplay might be between roll structure in the surface layer and possibly roll structure in the bottom boundary layer.
Oh, a great question. I haven't heard about the rolls in the boundary layer. But yeah, you're absolutely right that yes, ocean loses momentum to the bottom, so both with boundary currents, but also through wave motion, especially in shallow water. And wave models do account for bottom friction. So that is part of the terms, even though it was not shown exactly in my equations. But the relationship about Langmuir circulations and bottom boundary layer circulations, yeah, I'd have to think about it before saying more. I'm not sure if they would appear in the same environments necessarily.
Yeah, we found this situation while doing aerial surveys of the Great Bahama Banks, looking at whitings, which is how we were able to visualize the Langmuir-like circulation, and we were really struck by how dominant it was compared to the surface-driven. If you look at the direction of the tidal current, it would align with that rather than the local wind every time.
That's very interesting. Thanks, John.
Thank you.
John, I suppose. Thank you kindly.
Thank you all.